Welcome everybody to How Market is Moving Toward DC session. I'm Alessandro Iubini. In ABB, I'm dealing with market segment and in particular renewables, energy storage system and transportation rail. As you can imagine, all of them are full of direct current application. Thinking about the main megatrends nowadays are influencing technology, I would like to highlight you some that probably you also have in mind. Digitalization and 5G communication infrastructure, the energy transition to renewable and the connected needs of energy storage, more efficient and intelligent connected near-zero energy buildings, the mobility transition that moving us toward electrified vehicles. Worldwide speaking, there are rural areas still do not have access to stable electricity. Making a link between these trends and the major challenges the world is facing, immediately I think about energy efficiency and sustainability, with a consequent reduced usage of natural resources. After the deeper analysis, it's easy to discover that direct current is the technology that plays a key role in all of those trends and helps to solve these challenges. Associate direct current to PV, energy storage, and batteries used in everyday device is obvious. Let us discover more. 75% of lighting in 2025 will be LED lighting, so direct current. 80% of load in commercial and residential structure are now natively DC. 50% of the worldwide motor will be soon started through a drive, so also an AC motor could be supplied as a DC load. 90% less material in weight is required to modify the DC voltage level compared to a AC transformer, even if an advanced technology is required. Supply the direct current native devices directly with a DC distribution network saves conversion losses ranged from 15 up to 30%. So, direct current application seems to be very promising. In this session, we would like to share some contributions collected from people that has already started to deal with the direct current project. We will be able to listen by their voice the challenges they still have to solve and the benefit they have already achieved. Let's start. Lightnings. Nowadays, something we consider granted. We probably forgot how much our life will be different without it. I'm going to introduce you our first contribution from Vimal Mahendru, Chair of ESC Technical Committee, Low Voltage Direct Current, and ESC Ambassador. He will share his view about direct current evolution, starting from an interesting history. He will give us also an overview about the status of the ESC standardization activities around direct current.
Good morning and namaste, dear friends and colleagues. It's indeed a pleasure to be invited to speak at the IEC Summit. I'm Vimal Mahendru and I'm chair of the IEC Systems Committee LVDC and also IEC Ambassador. May I begin by telling you a short story about this gentleman whom I met in 2014. This was a village in 2014 which had absolutely no electricity. This man was sitting outside and weaving bamboo baskets, bamboo being a local resource. He would make about 10 baskets a day, and come sundown, there would be a stop to all activities, and he would move indoors and sleep in the dark. In 2017, thanks to a government grant, he got a solar PV panel on the rooftop, a small battery, a charge controller, and just one LED bulb. It transformed his life. Now he could continue to weave baskets once he was indoors. His output increased by 40%, and this was pure profit. This is the transformational value of direct current. DC is all around us. We don't realize it, but we even carry DC in our pockets. But the world has almost totally changed to DC. We did not even realize it was changing so fast. Even the USB stick that we use every day, it's nothing but DC. So that is the kind of power that we see that DC has. But why is DC re-emerging? Why do we see so much of direct current around us these days? And may I take you on this journey from the early days to the current situation? When electricity was first commercially distributed, that was by Thomas Edison. At that time, AC and DC were coexisting. The transformer was available. The main fuels were coal, oil, wood. Electricity was still a novelty and an elitist product, but it was not mainstream. Environment and energy efficiency were non-issues. The key technologies were AC and DC related network innovations and the electric bulb. And it was purely for the electric bulb that the initial proliferation took place. Then the two world wars changed the scenario. They required rapid electrification of the industry. AC began to dominate because it needed huge power plants. Coal, oil, hydro, nuclear fuels came up. Electricity became mainstream, and from an elitist product, every person was needing to use it. Energy efficiency and environment, even at that stage, were non-issues. The key defining technologies for this kind of growth were electric motors, AC systems, high power loads, etc. However, in the last 20 years or so, we've seen a big change. And the change is mainly because we find that solar PV, which was there earlier also, but because of the price rationalization and the cost coming down, solar PV has become more easily available. Electricity has become a basic necessity. Environment, energy efficiency are global agenda. The regulators, the UN bodies, policymakers all of them are looking at the sustainable development goals and the global agenda for sustainability. So the defining technologies are electronics, solar PV panels and solar PV technologies, batteries, LED lighting, and everything smart that we're doing. And guess what? All of these are direct current. And this is one reason why we are seeing a sudden explosion of use cases for direct current. But how do we define DC? I remember, and I'm sure you will recall from our high school textbooks, we thought of DC as a straight line. However, this is also DC, this is also DC, and so are these. The very definition of DC is undergoing change. A lot of different things are possible with DC, and this is exactly the work which is being done in IEC Technical Committee 8 and the Systems Committee for Low Voltage Direct Current, which I have the privilege of chairing. Over here, we are looking at the very basic definitions and putting parameters around power quality for direct current systems. This is the kind of structure that the System Committee LVDC has, where there are a lot of use cases that are being looked at and applications. There is a joint working group 9, which looks after jointly working and defining power quality and direct current related definitions. There are a lot of ad hoc groups and a chairs advisory group which are working together. There is also a LinkedIn group, which is a closed group of all those who want to contribute to the DC related thinking. And there is also the open forum, which is an IEC forum for all members of IEC who want to contribute to the development of DC. But let me also say that DC is a technology. It's not a product. Unlike a tire, which is by itself cannot move, but when you put it together in a car with all the other components, that's what makes it move. A car cannot move without a tire, but yet a tire cannot move by itself. Similarly, LVDC is a technology, it's a platform, and it should be seen as something which needs to be across all areas of using electricity. And that's when the real benefits of DC can be harnessed. Let me share also this unique story from India. The picture on the left is of this old lady who has a push cart in Bangalore where she is roasting corn. Earlier, she used to have a handheld fan, which is now replaced by a solar powered fan, which is directly helping her get the heat going and roast the corn. There is a small LED light also. Exactly the same application on the right side is in the smartest city in the world these days by some measure. This is Singapore. In Singapore, they have solar PV panels on top, and there are public fans where people can sit under for comfort. The same case, very different application. And then this is where I think DC is making a big difference to both. I have closed by sharing this slide with information on LVDC, and I hope this gives you a well-rounded information. Looking forward to success of the ICDC Summit. Thank you.
Thanks, Vimal. One point Vimal touches is digitalization. There are DC devices like PC, smartphone, tablet, appliances with embedded logics that became every day more present in our life and could benefit from a DC distribution line. If we take as example global USB-C market, USB-C devices are anticipated to reach over 5 billion pieces by 2022. Related 5G infrastructure creates the needs of high-efficiency and innovative DC power system that can tolerate high loads. The DC power system market size is expected to increase, reaching 1 million units by 2025. But move on. According to a 2018 report, the total annual direct current distribution network implementation spending is expected to grow from more than $11 billion of 2018 up to $48 billion in 2027. Huge growth, isn't it? Some challenges are still there. Some others are already solved. RSC is studying DC distribution since 2008, and in 2011 they have also realized a DC microgrid demonstrator. Let's Ricardo Lazzari explain us something more about their research.
Good morning, everyone. Welcome to the DC microgrid laboratory of RSC. I'm Ricardo Lazzari. I'm a research engineer and I deal with activity in the field of AC and DC microgrid. I'm the person in charge of the development and the experimental activities that involves our ABB laboratory. The RSC DC microgrid was realized in 2011, thanks to the support of the Research Fund for Italian Electrical System, and it allows the execution of experimental activity in the field of DC microgrid. In particular, through this grid, it is possible to develop and demonstrate control algorithms for the system operation and to verify the integration of DC grid components and protection devices. Our DC microgrid is unipolar, operates at a nominal voltage of 308 volt, and it is interconnected to the main AC microgrid by the means of a bidirectional AC-DC converter with a rated power of 100 kVA. In the grid are also installed several energy storage systems, like two high-temperature sodium-nickel chloride batteries with a nominal energy of 16 kWh and two supercapacitor banks, each one with a nominal power of 30 kW for 8 seconds. Each energy storage system are coupled to the DC grid through bidirectional converters to allow charge and discharge operation. In the grid are also installed a DC generator with a rated power of 20 kW that can be used to emulate a PV field, a resistive programmable load with a rated power of 30 kW directly connected to the grid, and another resistive load interconnected to the DC bus by the means of bidirectional DC-DC converter. All these components can be used to replicate the behavior of different systems, such as an industrial grid or a DC buildings. At last, a second AC-DC converter with a rated power of 30 kVA allows to mesh the existing AC microgrid and to control the power exchange between two different feeders. A secondary AC subgrid operating at different voltage and frequency level can be so fed by the existing DC grid. All the power converters installed in the grid are interfaced through the space controller, allowing the design of new control architectures and execution of different experimental activities. The DC microgrid has been used during this year in order to perform a research activity and explore advantages and disadvantages of this technology in respect with the traditional AC grid. The main advantages are the ease management of the power compared to the traditional grid and the better efficiency in case of grid composed by storage system, renewable energy sources and electronics load, such as electric vehicle charging station, LED lighting, and more in general, all the components that requires to convert AC to DC for the internal operation. The main limitations are related to the stability and the protection of such a grid. The DC grid is a converter-based system with capacitive components and low cable inductance. The absence of rotating electrical machinery and the spread use of converters reduces the system inertia, and the stability of the grid can be impacted by the presence of switching or intermittent loads and generators, and by constant power loads. Moreover, during full condition, the current in the grid is not limited by the cable's inductance, and the presence of capacitive components determines high peak of current that must be interrupted in a very fast way. For this reason, several activities and experimentation has been performed considering the control of each DC-DC and DC-AC converter in order to improve the stability of the grid, also in presence of constant power loads and during island operation. Moreover, different experiences have been carried out on the protection devices for such a grid. In particular, the novel hybrid circuit breaker able to interrupt a short circuit fault in few milliseconds has been designed, developed, and tested during our research activities. The development occurred in the last years on the technology for the DC grid, both at converter level and at protection level, has permitted to overcome almost all the limitations of this technology, and now the DC is ready to be spread out. I don't expect that the DC grid will substitute completely AC grid, but I think that these two technologies can be coupled together in order to achieve an higher efficiency and a more robust electrical system.
DC is ready to be spread out, was Ricardos' conclusion. For a researcher point of view, it's the time to start to combine direct current with AC distribution. If we look at distributed energy resources, one of the most promising and fast-growing segments, we will find a very good base to start to realize direct current distribution system. DC system, because of their constant voltage, do not need synchronization. Therefore, paralleling multiple layers in a DC system is very easier and requires no control. Thus, a DC system is uniquely suited for application where distributed energy resources must work together, like battery energy storage, photovoltaic plants, diesel generators. The elimination of synchronization, which can easily and reliably integrate layers in a DC architecture, is bound to encourage the use of direct current, since there is no need of complex control system, including algorithms and components, anymore. To go a little in deeper of ESS real projects, let's listen Giuseppe Artizzu from NGPS.
Now, let me outline one clear example of the developments that we are observing. Last year, ENGIE, the ENGIE Group, was awarded by the Guam Power Authority a power purchase agreement for the supply of renewable energy out of 2 solar plants for an overall capacity of around 50 megawatt to be delivered to the grid entirely after sunset. So full-time shift of solar production from 50 megawatt of solar generation capacity. In order to do so, we devised a system envisaging the installation of approximately 300 megawatt hour of storage capacity to be built using lithium-ion batteries. The moment 100% of the solar generation capacity solar energy will need to be delivered to the grid, not simultaneously with generation, so this entire energy flow will flow through the battery system. The double conversion that a normal alternate current architecture would imply is something that would have a material detrimental effect on the amount of energy deliverable to the grid, and therefore it would impact the revenue stream generated by the project for the independent power producer. Furthermore, since we are talking about a system located on an island with the obvious challenging of stability that very high penetration of intermittent renewables, in this case solar, implies, the Guam Power Authority was very sympathetic to the idea of having the solar system not directly interconnected to its alternate current system. And therefore, a second reason to consider a DC architecture was to decouple essentially the working of the solar system from the broader Guam grid. And this is what we have implemented. So the system is the architecture that we devised, coupled solar energy generation and lithium-ion battery storage on the DC side of the system, and then we have a DC-AC converter interconnecting the whole system to the grid. Now, we think this is a sign of things to come. With the decrease in the cost of batteries, that justifies the economics of larger and larger system and the ability to time shift larger and larger amount of energy. The effect of double conversion will be more and more significant, and therefore the benefits of DC coupling will be more and more apparent. We are working on a number of similar projects globally with different mixes of direct supply to the grid and time shift of energy, with or without provision of ancillary services, each one with different kind of challenges and priority. But broadly, we do believe that the trend is there, and more we are looking at technology partners that can help us improving the performance of our system with DC current architectures.
Thanks, Giuseppe. As you well explained, the need to support the utility in terms of voltage and frequency regulation and the capability to inject and absorb power in a fast way are enabling the increase of utility-scale battery energy storage system application. Consider that ESS has an expected CAGR of more than 20%. Furthermore, realizing microgrid coupling DC system component directly in DC, as well explains, offer many benefits and should guarantee about 30% operational and capital cost savings. It looks very promising. As promising is the application and the real project we are going to deep dive now. The utilization of the DC low voltage distribution open new possibilities for network development. For example, with the same voltage drop and the same cable size, a DC system of 1500 volt DC transmits 16 times more power than an AC system at 400 volt AC. Although AC voltage rating is currently used in its full capacity. DC voltage is still unexploited in distribution system. Component price of power electronics have constantly been declining in the last decade, allowing power electronic devices to be used in a greater number of applications. One of those is for sure manufacturing industry, where there are projects that aims to realize a full DC power distribution infrastructure. Thanks to Professor Holger Borcherding for the deep dive of direct current industry and Industry 2 project.
Hello, my name is Holger Borcherding. I'm Professor for Power Electronics, Electrical Drives and EMC at the Ostwestfalen-Lippe University of Applied Sciences and Arts. Today I want to talk about the project DC Industry. You see the label here and the name here. This project is in a second phase named DC Industry 2. And on this page you see an overview of the project. The project is funded by the German government, especially for the Federal Ministry of Economics. And the duration is 3 years, and we worked on this project until September 22. At the moment, we have nearly 40 partners of industry and research, and the objectives of this actual projects are to make a safe and robust energy supply by the use of DC grids. Several other objectives of the project are shown here, and I show you some details later on in this presentation. Especially in this project we have a lot of model plants. These model plants are to investigate the DC technology and to show other people that it works. Where do we come from? The normal AC grid is shown here. If you are in a factory, you see you have mostly a transformer, and this transformer connects the factory to the medium voltage. Later on, you see the AC distribution system. Very often it is a ground system which has been developed over many years in the factory. The consumers are, for example, complete machines, directly connected motors or frequency converters, and sometimes you have emergency power in case of faults in the medium voltage. Our vision is that we can change this topology via a DC grid factory, a DC factory grid. Our vision is that we can change this topology into an industrial DC factory grid. This grid consists, that is the main part of a DC mains. You see the value of 650 volts. It corresponds with a rectified 400 or 480 volt AC system. On the supply side, you have a feed-in, uncontrolled or controlled. Inside the DC grid, you have a lot of consumers. For example, machines, speed drives, variable speed drives, or passive loads, and especially 24-volt power supplies. The importance is that you can connect energy generators directly to the grid via DC-DC converters. The same it is with storage systems. You can integrate them directly, and storage systems have DC voltage inside, so it is very easy to connect them. We have one disadvantage, that is if you want to plug in an old AC device. For this you need additional power electronics. The advantages, there are a lot of advantages of DC grids for the industrial plants. You have a rising energy efficiency because the transformation losses are reduced. Also, you have a lower lower kappa, that means that you can reduce the transport losses in the DC grid. On the other hand, you can directly use renewable energy sources like a solar module on the roof of the factory. And another advantage is that you can reduce the peak power of the factory by the use of these storage systems. The resource efficiency is much better than in AC grids. You can reduce the use of copper by nearly a half, and the size of the equipment goes down because, for example, you have no rectifiers in the frequency converters and in all other devices on the bottom. Also, the connection of solar inverters and storage system is much easier. You have another advantage in the main stability because an uninterruptible power supply is integrated in the system. If you have a fault in the AC grid, then you can switch off the rectifier or the feed-in system, and then you use the energy of the storage systems to supply all devices below. Also, you can reduce failures in the AC grid. For example, if you have an active in-feed controller here, you have the possibility to control the reactive power or the distortion power. Industrial DC grids like this are very smart because all components work together to manage the power supply, and that means that you have an intelligent working of the DC grid installed by itself. On the other hand, you can support modular machine concepts because the loads are sorted, they are put it into group. I show you this later. Our DC voltage operates between 400 and 800 volts. That is because most of the old devices connected to 3x AC grids have an internal DC voltage in this area. That means that we can use a lot of actual technology and actual devices for this network. On the other hand, that means that our voltage area are fixed by the mains and the rectification technology. If you have uncontrolled rectifiers, for example, and a 400 volt AC network, then you have a green area, a nominal area between 485 and 625 volts. If you have uncontrolled 480 volts, or if you use an active in-feed converter for the system, then the green area is a little bit higher, between 585 and 750 volts. The yellow and orange areas are for the operation in case of switching of loads or in special areas of the grids. For example, you can use the yellow area too, but maybe you have to derate the power of the devices because of limiting of currents. These values comes from the rectification, I've told it, and we think that in most cases the right area will be used. To stabilize the network, we have rules in our specification. The simplest way is to have an uncontrolled operation, a basic network. That means that you have a very small DC grid, like in a single machine. So sometimes there's no control needed. For example, if you have a diode rectifier. But if you use storage system or regenerative energy, then the B and C controls are better. B is a decentralized group control. There, every storage system or generator has voltage-dependent setup value for the power of this device. These characteristics are non-linear, and the target is that the system goes automatically to the green area of our voltages. For example, if the voltage is too low or too high. You can change this characteristic curves by an extended control. For this you have to communicate with each device. But it's state of the art, it's very simple, because most of our consumers have a field bus connection at all. And if you want it, you can make a central voltage control also. The importance of DC industry is why several big manufacturers of Europe are inside this project. You see manufacturers with bigger parts in the project here, but if you look here, sometimes it's 80% of the European market in some areas. So that's the importance of DC industry. And with this amount of manufacturers, we are sure that we can make a standard from the specification of DC industry. Here's a picture of some guys in the project, and at the end I will conclude it. I've shown to you that DC industry is a system for the factory DC grid, and it has a lot of aspects to make the grid of a complete production hall. That means that you have specifications for a robust supply, you have services for the mains, you use decentralized energy, and so on. Our approach is to have an open DC grid system. That means that every manufacturer or every user can use the DC industry specification for the product or his factory, and therefore we hope that very soon the DC industry will become a standard, and my opinion is that we are on the way to the DC factory where all energy is exchanged via DC. Thank you very much.
Thanks, Holger, for this comprehensive overview describing this promising application. Maybe unexpected but true. Big industries, like automotive, are already testing the benefit of direct current infrastructure. But even in building, a lot of steps has been done, and also full DC building are becoming real. Asia Pacific and China are the leading market with growing need of power in this region. DC distribution systems have the capability of making power available to a large part of the population. The major trends driving this market are increasing in distribution efficiency, increasing demand for direct current-dependent architecture, the mismatch between renewable sources and demand location. Moreover, direct current system can work on variable frequency, and direct current architecture is simpler than AC, requiring less space, equipment installation, and maintenance. These characteristics make direct current technology appealing to customers, especially in the commercial sector. A special thanks to Bing Zhu, professor of the China Southwest Architectural and Design Institute Corporation. It will bring the experience of an upcoming building with a DC distribution system and zero net energy consumption.
大家好，我是中国建筑西南设计院教授级高级工程师、3院副总工程师朱斌，很高兴在这里给大家分享我们对民用建筑低压直流系统的研究。我将从项目概况、采用直流系统的意义，以及我们需要解决什么问题，系统实施的架构4个方面做分享。中国建筑西南设计院成立于1950年，今年是70周年华诞，地址是四川成都。它是被 RCC 评选为10大设计公司。西南院08年前在我们的第1办公区进行办公，2010年到2020年在第2办公区办公，第3办公区是我们正在新建的新办公楼，是我们设计院走向顶尖设计院的载体，所以说我们赋予了它前瞻性的技术——直流系统。这个项目总建筑面积7.8万平米，已经获得了近邻能耗的3星级绿色建筑，是整个建筑形式是一个模块化的一个建筑形式。我们利用了其中一个2000平米的模块做直流系统，直流机房和储能设备设于地下1层，我们利用屋顶做光伏组件。直流系统的使用在办公场景，我们利用有直流电脑、LED 灯、直流照明、风扇、加湿器、冰箱等等，以及有充电桩，还有就是48伏的体验设备、直流电伏试验设备、特斯拉线圈等的体验。为什么我们要设计直流系统？是源于现在电源侧大量的风电、光电，以及复合侧大量的直流复合 LED 照明、电子设备、电动车、电热等，采用直流系统可以减少中间环节，降低能耗。我们通过光伏的接入，我们实现了对太阳能可再生能源的利用。我们通过对储能的介入，我们利用低谷电压实现消防停谷，降低了运行费用，减少了变压器的装机容量。利用双向充电桩可以实现未来电动车对大厦进行反向充电，实现建筑的动态增容，可以降低我们建筑对市政电网的依赖。ABB 在双向电动车的充电桩的研究方面处于领先地位。另外，利用直流系统会更安全，因为它的安全电压根据 IEC 61140规定在120伏，所以说直流系统会更安全。我们要探索，我们要实现直流系统，我们必须要解决35个问题。其中这红色柱的问题，我们利用了 ABB 的技术来解决这30个问题，最终实现了我们的直流架构。这是光伏系统、储能设备、充电桩。 这是我们最后的实示图。我们利用 ABB 的断路器实现了整个系统。这个表里面的数据证明我们是近零能耗的建筑。我相信，为了趋势汽车电动直流化、建筑用电直流化，我们项目将于2022年12月投入运行。通过运行会有更多精彩。谢谢 ，Thank you.
Thank Bean for this explanation and for the clear messages about the state of the art of DC distribution in buildings. We hope to get soon feedback about the benefit this building will provide once in service. Speaking about building and infrastructure, we were able to see that even in Europe, and especially in the Netherlands, buildings with direct current infrastructure have been already realized. I'm glad to introduce you one of the predecessors of direct current system and prior actor in the standardization activity in Europe, Henry Stokman. With this contribution, we would like to collect the experience of a person that deals with direct current from a long time, and that will give us his vision and also for the upcoming future.
Hello, my name is Harry Stokman. I'm a DC entrepreneur, and my whole workable life focused on DC for more than 30 years. 16 years ago, I realized that the existing system will become incompatible with the new requirements we add to the system. The electrical system is our biggest asset we own as mankind. This worries me, because we have become completely dependent on it. This is why that I as a DC entrepreneur have asked myself the question, if we have the choice again, what will be the outcome? AC or DC? With the knowledge of today and the technology of today. As an electrical engineer, for me the outcome is clear. It will be a DC system. Because everything what we are connecting to the system is based on electronics, even so for the renewable generation, which is based on electronics. While the system is based on rotating energy. This is not compatible. Send and movement are not each other's friends. This was for me the big driver to develop a vision and a plan, based on the knowledge we have as a DC company, building rectifiers for industrial processes and corrosion control. In 2009, I've started the company Direct Current to make this vision realistic. We created from day one projects outside the lab with external installers and integrators. This was asking a lot of trust and guts. Our team has a strong mindset. We can do things that we have never done before. We did it this way because if we stay in the lab, we will only burn money and nothing will happen. It's better to make programs bigger. This will force solutions. On the moment of today, we provide around 300 km of public lighting, did 2 big buildings on DC and realized a microgrid with the size of 4.7 km, complete with generation and batteries and loads. The biggest conclusion is that the protocol is a must, and there are some gaps in standards, that different protection schemes are needed. This is why we developed for the DC zoning system, which became part of the Dutch national NPR 1990. The required protocol we have developed and we have validated this the last 10 years, based on the lessons learned from the projects. We call this protocol Current OS. The Current OS is covering all aspects that is required to build DC systems on the basic principles of the Dutch water system, where the big drivers are locally balanced, autonomous operation, using the both distribution system based on consensus. No digital communication is required to build the smartest grid. This means privacy by design, smartness, complexity to the components, and simplicity to the system, isolating mode, protection based on solid state, and a strict protocol to make this work. Thanks for watching and be welcome to the Current OS Foundation.
Thanks, Harry, for this valuable contribution. Really, DC systems are today reality. Time to conclude our journey. We hope you find interesting and helpful the application we selected for these first 2 days. We are conscious that a lot of applications are still missing, others are under preparation. So, just as a preview, we feel the need to anticipate a bit another promising application, DC Marine. DC distribution on board allows the use of variable speed generators, increasing their efficiency, which brings to fuel saving and CO2 and NOx emission limitation, according to the International Maritime Organization regulation, in a context of green ships evolution. DC distribution on board allows to reduce the size and the weight of electrical distribution switchgear. In addition, the driver for feeding and adjusting electrical propulsion are lighter and more compact. Just as an example, DC distribution on board of medium-small vessel allow 40% weight reduction and 80% less volume. From a study, this allows to save up to 30% of fuel. Thanks a lot to Peter Rampen from Damen for contributing to this event. Let's see from a true story how direct current is positively impact the shipyard sector.
Hello, my name is Peter Rampen. In my position as a Principal Research Engineer within Damen Central R&D Department, I'm leading a team of experts on the topic of electrification and automation. As a company, it's our aim to become the most digitally connected and sustainable shipbuilder in the world. We're already working daily on the topic of electrification. As a result of this, we're already using DC in our ships today. For example, we apply them on our full electric ferries operating in the city of Copenhagen and also on ferries operating in British Columbia. They at the moment are still working on hybrids, but in the future they are made to become full electric. We're also building the first full electric tugboat with 70 tons of bullet power, and have already delivered the first full electric gutted suction dredger. The main benefits of using DC at the moment is the easy integration of batteries on our ships. Furthermore, most of our main consumers are DC by nature as well. The switch to DC brings a number of benefits for us. For us, it's much easier to integrate the battery directly to the DC, and those batteries are very important to us to make our ships more sustainable. Also, a lot of main consumers are already DC by nature. The end result of this will be a more efficient system, also in reduction of sizes and weight and price tags of our ships. This is of course not without any challenge. As an example, integration of the auxiliary loads is still very difficult. There is still a lack of availability of components, and that's why it's so important that our suppliers are working so hard to make those components available for us. In the future, we would expect to see an increased amount of ships with at least partial DC systems. This accounts not only for batteries, but in the future we also expect ships to be equipped with fuel cells, which are DC by nature as well. I would expect in time to see plug-and-play DC grids with intelligent solid-state-based distribution equipment. This development will help us with our aim to become the most digitally connected and sustainable shipbuilder in the world.
This was just a preview. As I said, one of the scopes was also to invite you to share with us your direct current application and experiences. To do it, I would like to invite you to get in contact with us through icdcsummit.com webpage. As we saw many times, our aim is to create a network that starts today, but lets us to stay in touch, even in the upcoming week and months. icdcsummit.com will remain as a platform to interact, discuss, get in contact with our experts, propose new topics and find out more content, further live sessions, touching different topics or simply go in depth of a specific argument. Any question, doubt, really feel free to ask us and we will do our best to support you. Thank you for your participation and patience. This session was a bit longer than expected, but I'm convinced that we're valuable too. Many thanks to all our contributors that offer us their precious knowledge and support. Vivian, we come back to you.